Really, we start. Okay, I guess we can start, Andrea, right? Are you okay with it?
Yeah.
Okay, so welcome to everyone. This is NLB-based software engineering, NLBSE, the first edition of this workshop. And we are Andrea Di Surbo from University of Sagna and Sebastiano Panichella. This workshop has a main focus on putting together expert in natural language-based research and software engineering expert to solve software engineering problem, mainly toward development, maintenance, and evolution. A key aspect of the workshop, at least the way we, Andrea and the other members of the committee and the tool competition, we designed it, is to have a workshop that is a sort of a venue for tools, not only for research. Pretty much that's why there is a tool competition, to enforce researchers to have more tools being developed in the community and maintained over the time. Said that, we welcome anyone that would be interested to join the workshop. So, and we are also, inviting you to tweet about the workshop, any topic that you find interest during the talk of the keynote that will follow in a few minutes from Denis Porfianic, papers and the tool competition. So we're pretty happy if you promote a bit the research that is going on in software engineering, of course, pretended partially in this workshop. And if you want to share access to other members of your team, whether they're students, colleagues, pretty much you can access this short link. It's already shared on the chat. And Yang Seng and other members of the team will give access while this presentation is going, and also the keynote. Said that, little small rules, you know them, but it's good to remind. So for most of you that were registered, you got an invitation via Microsoft Teams. If you did not get that, of course, you can contact organizers. If you have a problem to access, or some colleagues of yours have a problem to access, just contact Yang Seng and other people that are organizing. They will try to follow you back to help you out to enter. Of course, while other people are presenting, the presentation, the discussion, of course, is good to have sort of formal modus where you wait the right moment. You maybe rise the end to make questions, so that in the sort of the presentation not interrupted to some extent. By that, of course, we expect to have the presentation in most cases live, so that people can actually interact immediately after during the talk. We have recorded videos for most people or presenters. So in case this does not work, we will run the videos. Of course, the idea is that the live presentation are preferred, especially in a workshop. So said that, we invite you to have to share or like raise your hands when you're interested to join a conversation. And of course, we'll try to give you voice. If you are not able to share your microphone or you're too shy, we can take questions from the chat, whether if this in here in Microsoft Teams. If we notice there are some questions even in mid-space, we'll try to gather from that and put in here in the loop of the workshop. Okay, so more interesting, the first edition on natural language-based software engineering was quite, there was a good participation from authors, and also we received a lot of papers on the research track, whether they were short paper, long paper, and whether they're also considered tool competition. We got got participation. So we want to thank you all that you are here, and probably some of the people able to join at the moment. It's interesting to see how they are very geographically distributed, a number of participants and the researcher. So most of them come from the United States, Germany, and Italy, but of course there are good representation from India, Ireland, New Zealand, and Netherlands from research paper. When we go to two competition, a subset of country are also represented there. There are Italy, United States, Germany, India, and Netherlands again. So thank you very much for making this workshop be successful, even before happening, with a lot of submission and a lot of research and tools that we can make it happen and having a good discussion. Of course, all this paper required a reviewing effort. Some of the people already joined here. For example, Nicole was here before. Thank you all for your effort. And here we have a really big team. I think very well distributed geographically and also in terms of gender balance, I think quite balanced. So we're quite happy that we had you and we had your help during the organizing and especially in the reviewing effort, which is one of the most important thing for the conference. So then we go on the meat of the workshop. We are on the opening, but in a very few minutes there will be a very exciting keynote from Denis Posivanic, and the topic will be on deep learning and software engineering from past, present, and future. Then there will be a short break because then there will be a longer session, a 1 hour, more or less a bit more of research paper. There will be 4 papers in this session, which will be between stakeholder flow analysis, but also understanding of identify names, but also generating trained data for question to cyber models. So they're very distributed topic. We expect to have a lot of discussion during this session. Of course, there will be then another break so that we have a good start, a fresh start to the 2 competition. Will be another 1 hour, more or less, where Rafael Callis and Oscar Chaparro will lead, will take the show of the workshop if you want, and they will lead the overview on what paper and tools have been received in the tool competition, what were the results. There will be, of course, the authors of the tool paper that will present, and there will be a follow-up discussion. So I strongly encourage all of you to join that part, a specific part, of course, any part of the workshop. That's a very key part of the workshop, which goes beyond maintaining and developing tools within the community. It's good to know what tools are led to the best results, especially in the issue this year. It was about issue classification of GitHub issues. Then will be a break, another break longer, again for having a bit of break, because before a final research paper session will be about natural language, very specific natural language based papers, but which also talk about systematic literature, so how to move forward from that. And then there will be the closing of the workshop. That's pretty much, I think, a very rich agenda that hopefully will entertain you. Well, let's start with an exciting keynote. So I'm really happy. I don't know if Dennis, you are able to enter the call meanwhile, but I'm happy to invite on the stage Denis Posivanic. He's a full professor in computer science at one of the most prestigious lab in software engineering, the Semero Group. We have seen a lot of research from him and his team on software maintenance evolution, program comprehension. Key aspect and key core technology was information retrieval, but he did much more research beyond that. And this resulted in a lot of awards that were figured in the most prestigious conference and the most influential papers. He has really influenced, at least according to us, a lot natural language-based software engineering of today, and of course, as it will be discussed during the keynote, deep learning research. He will talk about that, what was the past of it, what's actually the present and the future challenges. On a personal note, I think Denis Posivanic is a good reference for junior researcher. His research is not only proposing new theory, but also providing and delivering tools, which is more or less in the spirit of this workshop. So said that, Denis, I think I will leave the stage to let you present the keynote.
So Thank you, Sebastiano. Thank you, Andrea, for inviting me. Could you please confirm that you see my slides?
Yes. Yes.
You can see my
Yes.
slides?
Okay.
Yeah. Again, thanks a lot for, and you can see the, just let me make sure, you can see the transition, right? Okay, so super excited to be here. Of course, for some of us, it's very early morning, and this is the time when you know, when I think pretty well. So hopefully we're gonna have a pretty good discussion at the end of this talk as well. So as Sebastiano said, this is work that we've been doing in the past 10 years or so. And I've tried to put together some interesting story for you that would give you a very nice overview of what has been done. And I'll show you actually systematic literature review with some of the really nice nuggets extracted. I'll talk about some of the present work that we are doing. And of course, why we're here to discuss the future, right? What's next? So let me give you first a necessary introduction, and all of you might have heard about GitHub, right? Because GitHub Copilot, because machine learning clearly has been transforming many facets of our life, right? And like you've seen fantastic applications in speech and image recognition. You've noticed also that GitHub Copilot is transforming the lives of software developers, right? It's actually doing a pretty good job in terms of auto-completing a code. I actually have a student in my class who told me that he knows a startup team who actually wrote an Android app. Most of the code in that Android app actually was written using GitHub Copilot. And we'll talk about whether it's good or bad and what kind of issues you can run into a little bit later, but that's a reality. These tools are helping developers these days.
Just a second,
Okay?
Dennis, I don't think you see the screen. It's just me or Andrea. You also don't see the screen, the slides.
No, I don't see the slides.
Okay, they just disappeared a few seconds, and then it's...
Yeah.
Let me make sure you can see the slides. Can you see the slides now?
Now, yes, it just disappeared a few seconds.
And now you can see the slides, right? You can see the transitions, right?
Yes, yes.
Okay,
yes,
sounds good.
Yes.
So obviously, a lot of research in software engineering field has focused on automating many software engineering tasks, right? And all of you, or most of you, I assume, have written papers or have read papers, right, where we've used either machine learning or other approaches to automate many of these software engineering tasks, right? And this has been a very prolific research area in the past several years. Indeed, many of these solutions required manual feature engineering and actually expert insights, as you can see. In other words, if you were using typical canonical machine learning techniques, you would actually have to come up with handcrafted rules, which are based on some expert insights and defined heuristics to be able to do that. And indeed, these are some of the shortcomings of traditional machine learning techniques, right? You have to manually derive features. You are dealing typically with complex kernels, which can be very difficult to map and identify. And obviously that affects the ability to extract pertinent and important features from the data set. And when you use canonical or shallow machine learning techniques, typically you're dealing with shallow representations, which are limited to flattened vectors, right? Where you map these complex features of data to these shallow vectors, which obviously limits ability of these approaches. So thanks to massive growth of software engineering repositories, in particular, all those repositories hosting open source projects, a lot of data can be analyzed. And you all know this, right? Because by looking over the papers in this workshop, all the papers are using information from all these different sources of information. And thanks to truly amazing advances in modern computer architectures, we've seen really transformative effect that deep learning can have on software engineering research and practice, right? So where deep learning really thrives is when we have a lot of data where we can actually learn salient patterns to support many of these software engineering tasks. And indeed, given this, that deep learning allows for rich hierarchical feature embeddings. As you can see, the major difference between canonical machine learning-based approaches and deep learning-based approaches is that deep learning allows hierarchical feature embeddings, right? Thanks to this very important distinction, deep learning has been able to enable many different support for many different software engineering tasks by enabling automated feature discovery. Also, we've seen that automated feature discovery has been happening across many different types of artifacts. It's not just natural language, as this workshop is mostly concerned about, right? We've seen that other types of artifacts also have been successfully used for this task, like code or even images. Now, with all this in mind, let's quickly look into what has been done, or the past of deep learning in software engineering. So in order to give you a good overview of what has been done, in fact, recently we've performed a systematic literature review on using deep learning in software engineering research, which has been very recently published in TOSM. And in this systematic literature review, we focused on 5 primary research questions which are centered upon the components of learning. So we basically tried to scan hundreds of papers and answer various questions related to target functions, training examples, learning algorithms, hypothesis set, and final hypothesis, and basically all the issues surrounding that. So that's basically the scope of our systematic literature review. And on top of that, obviously, one issue that most of you are familiar with is reproducibility and replicability, right? And this is another question that we wanted to touch, just to understand to which degree some of these approaches papers can be actually reproduced, and what are the issues that we are facing when trying to do that. So in this systematic literature review, we actually looked into papers from 2009 to mid-2019, so this will not include this exponential explosion of papers that happened in between 2020 and 22. And I can tell you that from the fact, because when I'm bidding on papers for for ICSE or AEC, I see literally dozens and dozens of papers at the intersection of deep learning in software engineering, going both ways: deep learning for software engineering and software engineering for deep learning. So really, we see explosion of research interest in this topic. And kind of papers we looked into did not come just from ICSE, FSC, or other software engineering conferences. We also looked into some of the machine learning conferences that also published papers including software engineering topics like ICLR, NIPS, and a couple other conferences. And of course, we followed Kitcherman's methodology to make sure our own systematic literature review is actually reproducible. And this is something that we pride ourselves on. Hopefully that any of you can follow our process and get to similar results. And we've carefully explained our methodology in the paper, so that anybody can go back and reproduce the results of our systematic literature review itself. Okay, so now to the exciting part. What did we discover during the systematic literature review? Of course, we found that lots of software engineering papers publish on these topics, as you can see in this color map. But going to the first research question, target function. So what is a typical software engineering task that is being addressed in all these papers? Well, obviously we've seen dramatic explosion, right? And researchers have applied deep learning techniques to really diverse set of tasks, right? We're ranging from program synthesis, program comprehension, but source code generation, right? And truly, the list of tasks is very, very diverse. It's pretty much you pick any software engineering task these days, and you can see some sort of applications where deep learning has been applied. And of course, we will talk a little bit about whether that's a proper technique for that task or for that context. But this is something that we can discuss a little bit later. As far as data, training and testing data, our analysis found that researchers have explored a variety of different types of software engineering data in conjunction with deep learning techniques, where, of course, the main type of data utilized was source code. Like 60% of papers actually use source code as underlying data, input-output examples, natural language, of course, repository metadata, and visual data, right? And for example, we identified that software requirements, dependencies, and software licenses actually is type of data that has not been actually looked into when using deep learning. And obviously, we see a lot of room to combine different modalities of artifacts to create new types of rich data representations. On data pre-processing or processing side, our analysis found that a number of different data pre-processing techniques have been utilized. We found that obviously tokenization is used in approximately 40% of the cases, neural embeddings, 26% of the cases. These are two most prevalent data processing techniques. But also we found that data pre-processing is tightly coupled to the underlying deep learning model actually utilized and software engineering task, right? Also, we found a couple interesting things, like almost 1/3 of our analyzed studies actually did not perform any type of exploratory analysis in order to combat the confounding factors such as data snooping or bias, for example. And obviously, that's one of the problems. We do see lots of very shallow applications of these approaches without necessary domain knowledge. Also, some of the most popular mitigation techniques employed were different, were detailed analysis of the duplicates found within the training and testing set, and the use of validation set to prevent tuning parameters of the model to best perform on the test set, as well as removal of restrictive data filtering in order to extract data sets that are diverse as possible. So, in other words, some of the, for example, recent research by NLBSE that shows that you have to be very careful about duplicates in your training set. We already see a lot of impact of that research on how developers or researchers actually apply these techniques. When it comes to learning model, algorithm, and hypothesis set, our analysis revealed that basically we have 7 major types of deep learning architectures that have been used in this research space. Of course, we see that RNNs, recurrent neural networks, are used most of the time in 38% of the cases, encoder-decoder models, 18% of the cases, convolutional neural networks, feed-forward neural networks, and also autoencoders. Obviously, RNNs and encoder-decoders were most prevalent architectures. But again, we also found very strong correlation between particular deep learning architecture and data type, right? When, for example, architectures capable of capturing temporal differences with sequential data. For example, you use them to study source code, natural language, repository metadata, and then maybe program input-output examples, right? And architectures capable of capturing spatial and structural features from the data have been used primarily to study images, bug reports, and various other program structures like abstract syntax trees, control flow graphs, so forth and so on. So you do see a very strong correlation between type of the architecture and type of underlying data. So this is just yet another view of deep learning architectures across different software engineering tasks. Here our analysis also revealed 4 different techniques for updating weights in deep learning-based models, with obviously large majority making use of gradient descent, but also we found some other techniques or major techniques for calculating errors like cross entropy, negative log likelihood, maximum log likelihood, and we observed 4 major optimization algorithms, including eta grad, eta delta, and a couple others. So in order to combat overfitting, which is obviously a problem that you have to be paying attention to if you're using deep learning, we've seen that dropout was used in 16% of the papers, and this was the most commonly used methods to combat overfitting, followed typically by data cleaning 8%, L1, L2 regularization 8%, and early stopping 6%. And obviously what was not great is that almost 25% of the papers did not even discuss such techniques. Okay, so and you can guess for whatever reason, but that's obviously a problem, right? As far as final hypothesis or results, our analysis revealed that typically we have a general lack of well-documented reusable baselines or benchmarks when you work in this area. So as you can see, for example, from this chart, majority of the baseline techniques utilized in the evaluations of these study techniques were self-generated. So typically you would come up with a data set to actually to evaluate your technique on. And unfortunately, in many cases, as you can guess, the data was not available or reusable. While we have a subset of benchmark data sets that do exist for certain tasks, and there are some very promising benchmarks like from Microsoft, CodeGlue, and a couple others, there is a need for well-documented and vetted benchmarks. So our analysis also illustrates that a variety of metrics have been used to evaluate these techniques, with accuracy, precision, recall, NF measure obviously being most prominent. And in terms of claimed impact of primary studies, the most claimed was increased automation or efficiency, as you can guess, right? So this is kind of the main contribution that these papers claim, typically followed by claims of advancing deep learning-based architecture or customizing it for a specific task, as well as trying to replace human expertise outright. So another important consideration that when it comes to using deep learning-based approaches is whether you should be using deep learning in the first place, right? And some of you may be familiar of this paper, Easy Over Hard. And in fact, we found that most of the papers in our set did consider the concept of Occam's razor and offered a comparison to conceptually simpler learning model. Okay. And this was actually very positive because in most of the papers there was clearly demonstrated need for a more sophisticated or complex solution that would use deep learning versus some sort of simpler, shallow or canonical machine learning based baseline. So going to reproducibility and replicability, our analysis actually illustrates that only 15 of our primary studies could be conceivably labeled as replicable, whereas only 56 studies could be reasonably reproduced based upon description in the study. So this is fairly, unfortunately, this is fairly low percentage of the papers that we looked into overall. So and this slide demonstrates various reasons why it would be very hard to reproduce the results, because the papers were either lacking details about learning algorithm, hyperparameters, embedding details, or how exploratory analysis was done, or how filtering was done, or which loss function was used, how training, validation testing was done, whether regularization techniques and which techniques have been used, so forth and so on, right? And in addition to a lack of published open source implementation in data sets, obviously, the major contributing factors to these issues were mainly due to the missing data filtering details, almost 54 papers, and lack of description of hyperparameters, 38 papers. And if you worked in this area, you know that hyperparameters are absolutely critical. If you don't have those details, you probably is not going to be able to reproduce. So the actionable outcome of our systematic literature survey was actually guidelines that we compiled and designed for researchers who enter this field and would like to use deep learning based approaches to support software engineering tasks. But at the same time, we wanted to help these researchers and practitioners to avoid all these pitfalls that we've uncovered during the survey. So if you look into in our paper, you'll find these detailed guidelines that hopefully can guide you in a flowchart manner in terms of how you should be applying deep learning based approaches. And if nothing else, these guidelines will save you lots of potential reviewer criticism that you're likely to get if you obviously miss some of the important steps. Okay. So with that, this basically concludes very briefly the past, what has been done and what kind of issues we've identified. Now let me show you a couple of different approaches that we've been working on in our lab, and I'll try to show you two completely different data modalities. One modality, and of course, I'll pick two different examples that come from completely different stages of software development. But just to give you an overview, in our lab, we've been working on quite a few different problems where we've used deep learning to automate the support software engineering tasks ranging from mobile application design, code completion, clone detection, supporting code reviewing process, program repair, generating assert statements, generating mutants, reproducibility of bug reports, and also traceability link recovery. And I'll focus on two examples from these two different software development stages, design and maintenance, that would involve also two different data modalities. So when it comes to design, we'll work with visual data, and when it comes to maintenance, we'll work with natural language data. Okay. So let's look into the first approach, and this one involves basically helping developers to design graphical user interfaces for mobile applications. And I don't need to motivate this research space a lot to you. I know many of you have written papers in this space, but you know that a lot of tasks these days are done on mobile phones, and we actually have a lot of power users these days. One of my collaborators actually, running research tools on the phone, like editing papers, so forth and so on, which obviously is not what I would do. But also, you can see that these marketplaces offer a lot of apps these days, and one notable thing is that these applications are becoming of very high quality, or these applications typically have high quality graphical user interfaces to make sure that these applications actually can stand out from competition, right? If you look into certain categories, you can find, I don't know, 20 or 30 different weather applications, right? And one way to distinguish yourself from competition is actually to have a high quality graphical user interface. So when we actually look into how graphical user interfaces are designed for these commercial applications in industry, and this is something that we've done by actually working with an industrial partner, we actually found that graphical user interfaces are typically designed by a dedicated designer team. Graphical user interfaces for serious applications are not done by developers. They're done by designers, okay? And these are people who are highly creative, right? They use tools like Photoshop or Sketch, and typically they are responsible for expressing coherent design language across many facets of companies' digital presence, like websites, applications, digital marketing materials, so forth and so on, right? And typically the way this design/development process goes is that design team produces an initial sketch of the design, and then they send it to the development team. And development team takes this Photoshop-based sketch, or there is a tool that is actually called Sketch, which has Markdown plugin, where you can actually get a lot more information about the design. But the idea here, developers take this initial sketch and then they try to translate it into the actual application, right? So they basically look into the sketch and they say, oh, this is a button, no, this is this type of a GUI element, this is that type of GUI element, and this is how I instantiate it in the code, okay? And this all sounds great, right? Because developers typically look into the sketch and they have a lot of domain knowledge, right? They have understanding how to instantiate this design in the code. But the problem is actually when they do this initial version of the application and send it back to designers, most likely designers are going to find the problem, right? They're going to find some sort of design violations, or maybe incorrect types of GUI components that have been used, so forth and so on. And in practice, this is a very iterative process, okay? Very iterative process. So basically, for some serious applications, it may take dozens of iterations to go through this process before an initial correct version of GUI is actually implemented. And what makes it even more complicated, during maintenance, right? This GUI can be significantly revised, and it also needs to be updated. So these are real problems. In fact, one of our studies that was done with industrial partner shows that there are many different types of design violations that can actually happen in the field, right? So in that iterative process that you've seen, there are many different problems that can happen. So one research idea that we had was how can we actually try to warp this iterative process into one-step solution where ideally we could just take the sketch from designers and try to implement this GUI automatically, right? And you would think that, well, I mean, maybe we can just use machine learning and we can just rely on graphical data. And I'll actually show you our solution and I'll talk about some of the details. And you will see that you may actually need different types of data modalities to address this particular task. So of course, there is some existing work. This is a fairly dynamic area. In addition to some of these academic papers that we found, we also found a couple different startups that work in this field. But the main distinction is that these solutions are fairly limited in their ability to produce adequate GUI prototypes. For example, technique on the left, Rimawi, uses heuristics to generate app hierarchies, which is limited only to a number of concrete scenarios. And text-to-code, that's a technique that uses neural machine translation, requires domain-specific language and also works in fairly limited contexts. So in order to answer this question, we wanted to look into how developers would actually translate this GUI mockup into the code. What are the low-level steps that developers would take to address this task? We noticed that in the first step, they would detect or identify these GUI components that exist in the mockup. In the second step, they would classify these GUI components into their constituent types. And finally, they would assemble these GUI components into hierarchy, and then they would stipulate types to produce the final prototype. So in order to do that, we designed a fully automated solution which is clustered around these three steps: detection, classification, and assembly. And again, this is a fairly involved engineering solution that basically combines mining software repositories, dynamic analysis, computer vision, deep learning, and data mining to accomplish this task fully automatically. And on top of this, I would like to highlight in this piece of work that deep learning was absolutely essential part of this deep learning framework, of this redraw framework. So in other words, you couldn't just get by using, let's say, canonical shallow machine learning based approach like SVM with bags of visual words, because it would not give you the necessary accuracy to tackle this particular task. So I'll actually show you experimental results that clearly demonstrate that deep learning was absolutely necessary piece, just one piece of this fairly involved engineering solution to actually address this task. So let me now very briefly walk you through all the stages so that you have an intuition how this solution works in concert. So in the first step, we get an input from designers, which could be basically drawing on a napkin. Of course, we don't deal with those kind of inputs, but let's say it's a drawing in the Photoshop, right? And in this case, we use computer-based detection algorithms to identify bounding boxes of these likely component types. So the output of this first phase are just bounding boxes where computer vision will tell us there is something here, there is a component type here, we just don't know the type, okay? If you do work with sketch-like inputs, for example, many Android designers, they create designs using Markich, which is a plugin for Sketch. And typically, these allow exporting data in HTML and JavaScript. So for that, we actually designed a parser where we could get exactly the same data, but much more accurately, right? Without using any computer vision. So if you have the sketch-based mockup, we would be able to get basically coordinates of bounding boxes fairly precisely just by parsing JavaScript and HTML. Okay. So the second step, this is where things get much more interesting, right? Because here we have these bounding boxes in this mockup, but we don't know the component types, right? So here we decided to rely on machine learning, and in particular, we use deep learning-based technique, which is known as convolutional neural networks. And as you know, CNNs basically have been used in different contexts, and in many of these approaches have reached human levels of classification accuracy, right? I'm not going to go into excruciating detail, but at the very basic level, basically an input to convolutional neural network is an image that would be decomposed into an array of matrices or a tensor, where each matrix essentially represents the intensity of one of the color channels of the image, right? And then what happens in CNN, so you have a filter, a kernel, to the first convolutional layer that will be applied to this tensor, and it's going to slide across the matrix, and it's going to perform all these convolutional operations to transform the input matrix into the new matrix that would capture some of these abstract image features, right? And this process is going to be repeated through the different layers of the network, and between each layer, you're going to have a set of weights that will basically capture the importance of the features that are going to be extracted at each layer, right? And after one single pass through this network, we see that basically, unfortunately, it's going to give us an incorrect classification. So as you can see here, it says this is a text view, which is incorrect because this is a image button, right? So it gives us incorrect classification. So in order to deal with that, we actually need to calculate the error gradient, and then we need to backpropagate this error through the network to adjust the weights between the layers so that next time the network can actually make correct classification. And the idea here is that we're going to train this network on thousands or hundreds of thousands or maybe millions of data points so that it becomes even more accurate, right? So this all sounds good, right? You probably have seen CNNs before, but in the context of our task, $1 million question, right? Where do we get a lot of training data to train this convolutional neural network to do this task automatically, right? Because as most of you know, when it comes to applications of deep learning, it's all about data, right? Where do you get the data? Like in our case, where do you get a lot of data? So in our case, the solution was do a lot of work. And this basically involved a combination of mining software repositories and automated dynamic analysis. Essentially, what we've done, we built a crawler that helped us to mine thousands of APKs from Google Store and also some other open source repositories. And we also implemented a large-scale dynamic analysis infrastructure that we call execution engine that essentially utilizes systematic automated input generation approach that is based on our prior work. And in particular, basically what it does, it navigates target application's graphical user interface in depth-first search manner to basically exercise all tappable, non-tappable, typable, so in other words, capable of accepting text input components. And during the systematic exploration, we basically used Android's UI Automator framework to extract all the GUI-related information as XML files. So basically, for every state of the application, we would get detailed information as far as GUI hierarchies that would include information about the objects, types, and coordinates. So that's how we were able to basically produce a very large training data set of labeled images that would basically say these are different component types, and these are exactly the types and coordinates from actual screen. So the training data in our case was almost 200,000 labeled GUI components after data cleaning. Of course, in order to do that, this required even more serious effort to build execution engine infrastructure. And I'm not going to go into details, but the bottom line is this part of the project took us 80% of the effort, right? So sometimes this is just to note that the parts that take most of the time literally take 2 paragraphs in the paper. But I just want to highlight that from engineering point of view, this was truly massive amount of work to make it actually happen. So in the third stage, once we know these types of components, presumably, that CNN will give us, we would actually construct the GUI hierarchy. And the way we would construct the GUI hierarchy is actually by mining all the real GUI hierarchies that we've extracted from all these APKs, from thousands of these real-world APKs, and we would try to match some of these types that CNN would return us for these bounding boxes with real GUI hierarchies that we found in these applications. So the idea is that we would stitch a resulting GUI hierarchy for our mockup by using bits and pieces from real GUI hierarchies from real applications. And for that, we actually use data mining and KNN-based clustering approaches to accomplish this task. And again, this is going to be an iterative process where we would scan parts of the GUI hierarchies to find bits and pieces that basically match our inputs. And finally, we would put final touches on the prototype and assemble the application. So I'm not going to go into all the experimental results, but I'm going to show you one important piece, why deep learning was very critical here. And again, this shows you some of the experimental results, number of applications that we've used, number of unique screens, labeled GUI component images. And as a baseline, so our Occam's razor was that we used the support vector machine, which was based on bags of visual words. And at the very high level, essentially, this approach extracts image features using the speed-up robust feature or surf detection algorithm, and then uses k-means to cluster similar features together. And then it utilizes essentially SVM trained on resulting feature clusters. So as you can see, for our baseline classification results are not that great. So basically, we have 65% overall accuracy. And let me explain why this is not great. So if your input, if 35% of the time you're going to give me incorrect classification of the type of the component, and I'm going to use it as an input to the data mining clustering algorithm, basically it's going to give me a lot of noise as an input to that final step. So I have very little hope that my final GUI hierarchies will actually reflect the mockup. So this is not an accuracy that we can put up with. On the other hand, CNN-based classifier allows us for approximately 91% accuracy, okay, which is much, much better. So we have a much smaller error rate. And on top of this, we actually looked into why it's 91%, why it's not higher. And some of the results made a lot of sense. For example, if you deal with different types of components like progress bars, probably you know that there are different types of progress bars, right? There are those progress bars which are very, very short in Y direction and very long in the X direction, right? And there is a second type of progress bar, which basically is like a square progress bar that basically renders the progress well. And obviously for CNN, given these two completely different styles or shapes, it was very difficult for CNN to distinguish between drastically different images and learn a coherent set of features to differentiate between the two. However, the good news here was that if you look into the confusion matrix, it will show you that these misclassifications are typically skewed towards very similar classes. So for example, image buttons primarily misclassified as image views, and edit text are misclassified as text views. Right? So basically, from the developer point of view, given that these misclassifications were very close to relevant classes, it would not be a lot of work to do some quick manual fixes. So basically, this shows you why deep learning was absolutely necessary here. It was very difficult to use canonical shallow machine learning-based approaches to address this task. We also looked into some of the results with developers, and developers actually liked it. We got really good feedback from developers from Google who gave us some ideas that we implemented later on. And this basically shows you just some examples of what redraw is capable to generate. The original application on the left-hand side, and redraw based mockup is on the right-hand side. So, and you can see that we have results for different types of very famous applications. And this paper was published in IEEE Transactions on Software Engineering a couple years ago, and we presented it at FSC. So now let me move into a second task that I wanted to highlight, which now deals with natural language information and typically happens during software maintenance. So as we all know, source code evolves, right? And in order to evolve source code, developers need to perform software maintenance activities by transforming existing source code using different types of changes, right? And developers do corrective operations, which are aimed at fixing discovered problems, right? Like in this case, you see that null check is added before invoking the method on the variable myList. Also, developers do adaptive changes. So instead of to make sure that software product usable in a changing environment. They also do perfective operations to basically make sure it's maintainable. Like in this case, they added the Java duck to the method to make sure it's understandable. And also they do preventive changes aimed to detect and correct latent faults in software product before they become real faults. So all these types of changes are code transformations. So we're going to be referring to all these types of changes as code transformations. And developers perform hundreds of these code transformations on a daily basis. If you don't believe me, just go to all these version tracking systems and you will find literally millions of instances of these code transformations everywhere. And this is also for us a blessing because we can actually mine all the data to be able to train some of these approaches to hopefully do this fully automatically. And that's exactly was the goal of this research project, to be able to learn some of these code features automatically so that we can extract some of these salient patterns to be able to apply these transformations fully automatically. So again, if we have the code before and we have instances of the code after, our premise was that we can rely on techniques such as neural machine translation to learn from hundreds of thousands of instances of these code before and code after to be able to do these transformations fully automatically. And I don't need to convince you that neural machine translation has made tremendous impact in real life. Like just go to Google Translate and see how well it does translation from different natural languages. Similarly, we wanted to see if these techniques can be also used in source code context. And again, these techniques are typically encoder-decoder architectures, which in this case consist of two recurrent neural networks, an attention mechanism that basically lines target with source code tokens. So as far as the data for this project, we didn't just want to go and grab any data, any changes, right? We wanted to be able to train these approaches from meaningful changes done by the developers. In order to do that, we actually looked into the code review data. And as you know, developers need to perform, obviously, changes in the code, and rather than committing the changes directly to the master branch, right, they typically create a new branch. And they perform necessary changes in that branch. And once those changes are completed, they basically perform a pull request, right? And usually that pull request undergoes code review, where other developers are going to examine those changes and maybe leave comments, right? And that could lead actually to more changes and adjustments in the code. And then finally, once this code passes code review, then the pull request is accepted and the code is merged into the branch. And this is basically what we refer to as complete and meaningful code change, which has been reviewed and accepted. And obviously, this is a common process at many major software companies these days. So an important question that we ask is, can we actually automate this entire process? Okay, and the answer is yes, in part, but not obviously not fully. And in order to do that, I'm going to quickly show you some parts of this approach, which is based on mining code changes, extracting transformation pairs, abstracting code, which is a necessary step when you deal with neural machine translation approaches in very large vocabulary. And then I'll show you some of the very interesting results or types of examples of code transformations that these models were able to learn. So again, we're going to train these models only on meaningful code changes, not just any commits. Okay, so we're going to train them on the data that is coming from pull requests, which have been complete, reviewed, and accepted. Okay, so in order to do that, we've created our crawler for Garrett, which is a code review system, and we've basically extracted this data from approximately 339 projects from these project ecosystems, from all the pull requests which have been reviewed, accepted, and merged. And for basically for every instance, we took the file before, and file after. And we've also used basically tools like Gumtree diff in this case to perform method mappings between before and after versions of the same file. So basically, Gumtree diff is going to perform the mapping using semantic anchors, basically, which works even in the process of many changes. And then for each pair of methods, we perform AST differencing and extract the list of AST operations which have been performed between this version and that version. And for example, in this case, an if block was added in this method. Next, we consider only the method pairs for which we detect an AST operation and discard all the remaining. And we refer to this method as transformation pairs that basically formally represents this method before, method after, and the list of AST operations which have been performed in between. And we'll use these transformation pairs as an example of how to translate the original method into a changed method. Again, I'm not going to go into all the reasons why we choose the method level of granularity, because there are pros and cons, and of course there are limitations to what we can do with it, but this was part of our design. So as you know, because this is a natural language for software engineering workshop, right? We have lots of unique words in English dictionary. But what all of you know, and I don't need to repeat it many times, developers are not constrained by any vocabulary, right? Because like in our set of 339 projects, we found 370,000 unique words in our data set, okay? So when you try to train neural machine translation approaches with this kind of vocabulary, you may run into problems unless you have very powerful hardware. So in order to tackle this problem, we devised a process which is called code abstraction. And the goal of this process is to significantly reduce the vocabulary to be able to effectively train these models. So let me show you very quickly how code abstraction works in our case. Given the source code, we generate corresponding abstracted code in the following way. So first, we keep all the Java tokens and separators, since they're limited in number, and we want to generate syntactically correct code. Then we keep identifiers and literals such as size, and 0, and we call them idioms. And then we replace all the remaining identifiers and literals with the typified IDs that essentially represent the type and role of the source code, like method 1, variable 2. And regarding this typified ID, basically we use combination of lexer and parser to identify the type of identifiers and then substitute them with reusable ID. So this is basically an example of this abstraction process where first we take the code before the change. This becomes an input to our model. We do the abstraction. We keep all these details in the lookup table. Then we feed it into neural machine translation model, which is going to also produce abstracted changed code, which now we need to concretize. So basically, we need to generate real code that hopefully would be also compilable. And the way we do that is by going back to the table where we have all these mappings so that we can grab actual IDs and generate the code. So once all this data is prepared, now we can train our neural machine translation approach. Again, I'm not going to go into all the details. You can find them in the papers, but it's very important to point out that you know, we tuned hyperparameters. We controlled for overfitting by observing loss function on the validation set, and we, for example, selected configuration with best performances on the validation set. Instead of going through all the experimental results, let me show you the actual instances of what the model was able to learn. And to do that, I'll show you some instances from the taxonomy of all the transformations that the model was able to perform that are classified into 3 types: bug fixes, refactorings, and other types of changes. So as you can see, the most common subcategory is the one involving method invocations and parameters. But we also have changes, for example, involving conditional statements, exceptions, values, and lock mechanisms. As for the second category, refactoring, we can see that most frequent category are those changes related to, for example, readability of the code, but also naming conventions or inheritance and also encapsulation. And as far as other changes, they involve changes to method signatures, adding, deleting, and replacing code, as well as type and initialization changes. So these actually, this is a real example of refactoring where an anonymous class is replaced with a lambda expression, and the model was able to perform this change fully automatically, and it actually matches the change that was performed by a Vert developer during the transition of the code to Java 8. And this is yet another example of refactoring, less sophisticated, but you can see here that the model was able to merge two catch blocks into one. It's also important to point out that we've applied neural machine translation to other software engineering tasks like program repair, even mutant generation. And this is an interesting one because it may be a little bit counterintuitive. Because here we would train the model not by going from original code to fixed code, as you will find in the repositories, but here we would train the model in the reverse way. So we would actually try to train the model to generate bugs, right? And that's essentially the purpose of mutation testing, to evaluate the quality of the test suite. And here we would train the model to go from fixed to buggy code. To generate real-world mutation operators. Also, we've applied it to the task of generating assert statements. It's also very, very important to highlight here that when it comes to applications of these neural machine translation approaches to these different tasks, it's not as simple as, okay, here's a task, let me get the data, let me train the model, task solved. That's rarely the case, because in order to actually solve this task, you need to plug in many cases, in pseudo domain-specific analysis, right? Like in this case, for a third generation approach, we actually need a domain-specific analysis for identifying focal and test methods, okay? And this is pretty much the case for any software engineering task. So it's not as simple as, let me get the data, train the model, task solved. You have to, if you are designing a real approach, you have to do a lot more engineering and bring in a lot more engineering related to plugging in domain-specific analysis. Also, recently we explored some of the hot architectures like text-to-text transformers. Again, I already see the papers in the program, so I'm sure there will be a lot of discussion around it. But basically, what we've done in this work, we've pre-trained T5 on very large data sets like CodeSearchNet, which contains more than 2 million of methods, and some standard English text. And then once we pre-train the model, we also fine-tune it on smaller specialized data sets which are related to specific software engineering tasks that we want to address. And it actually eye-opening to how effective T5 can be when we compare it to some of the baselines from our own papers, like for program repair. You can clearly see that T5 gives you a lot of mileage by just training this model on generic code and English, and then fine-tuning it on program repair specific data. So you see that you get a lot of mileage as compared to the original benchmarks, both for small and medium methods, like in this case. You also can see that for third generation, while you may not see a lot of mileage here when you compare T5 to baseline when you do it on abstracted code, a really interesting case here that when you do T5, even without any abstraction process, you can get similar results, whereas your baseline is going to be significantly hampered if you don't use an abstraction process. We also use T5 in the context of supporting code reviewing, using different scenarios. Like in this scenario, for example, we've trained the model, given the code and the comment, to actually generate the code. So this would be the situation where you have your initial pull request, somebody else gives you the comment, and then the model would actually generate the change for that code given reviewer's comment. Like in the case that you see, this is the first case. You see that we have the code, and then you have a comment from developers suggesting object details, check for nulls, and that's exactly what the model was able to implement. And in the second case, basically the comment says else is redundant, and the model was able to remove it. These are a couple examples for different scenario where we go from code to comment. So this is as far as the present. Now we have a little bit of time, and I want to talk about future work. So where do we go from here? Obviously, this is part of this workshop to figure out where do we go from here. But needless to say that intersection of deep learning and software engineering has been a very hot topic, right? And this is why National Science Foundation actually asked us to do a workshop a couple of years ago on this topic. And we looked into many different challenges across two different directions. Deep learning for software engineering, and that's what I've been discussing up to this point. But also the second big area, which is software engineering for deep learning, basically which is viewed as a new form of software development that needs new tools and process support, where we are building systems that have deep learning-based components in them. So some of the future research directions for deep learning for software engineering are indeed quite a few. If you're interested in more details for these future directions, you can actually find them in the workshop report, and you can find that workshop report on my website. If you go to my homepage, you will actually find the link to this workshop report, which is more than 20 pages of details on some of these future research directions. But just to highlight a couple of them, one very obvious direction is to combine features that we learn with deep learning with existing empirical knowledge. And again, we've seen very good progress of incorporating knowledge into these black box deep learning models to explain these models, right? For example, this particular work leverages deep learning to discover representations of Koopman eigenvalues from data. And this work comes from mechanical engineering domain, right? But it shows you how you can benefit from the power of deep learning while retaining the physical interpretability of Koopman embeddings. So this is actually very eye-opening how some of the discoveries can be made using deep learning techniques by relying on some of the domain knowledge. We can actually use some of these ideas in a very similar way in software engineering context, right? We have a lot of very useful knowledge that came out from empirical studies, especially in the recent years, that now we can somehow encode into meaningful knowledge that we can actually plug into some of these pipelines. You may ask, give me an example. Okay, one example that comes to mind, for example, developing a code-specific, for example, byte code embedding, byte pair encoding algorithm, or BPE algorithm that would actually take into account, for example, underlying properties of source code, which are based on filtering vocabulary or how we split words or how we do subword splitting, right? You can actually design custom algorithms that will be part of your pipeline that would encode valuable knowledge, perhaps of the domain that you're working on or some other general properties. So this is just one example how we can use unique capabilities of deep learning models to automatically learn patterns without ignoring all this important knowledge that we've gathered and accumulated through the studies over in the recent years. Again, there are many other directions that you can see here, including leveraging and combining heterogeneous data sources, customizing architectures, so forth and so on. But one really important direction, in my opinion, is interpretability of these neural language models. Because as all of you know, again, GitHub Copilot is used to write production code these days, right? And it's based on these truly massive, large-scale neural language models, right? I don't know if you knew, but for example, Codex model, and this is what Copilot is based upon, has over 12 billion parameters. And it was actually trained almost on the entire GitHub, okay? And while we've made a very good progress on understanding general efficacy of these neural language models, we really don't know what is going on inside of those models. What kind of knowledge, what kind of properties do they capture? And this paper actually really opened my eyes, right? Because they basically show that Copilot generated a lot of code that had security vulnerabilities, okay? So, I mean, if you're gonna use these models blindly, right, you may end up in trouble like that, okay? And obviously, this community knows that there is a growing skepticism regarding utility of current automated metrics for natural language understanding generation tasks, right? So there are lots of complaints about blue metrics, right? There are lots of complaints from reviewers these days coming about using blue metrics on code, right? Many reviewers say, well, use code-specific metrics, right? That will capture syntax and semantics of the code. And again, we see a lot of the skepticism. So one of the areas where my lab is trying to work recently is to design some of the approaches that would kind of help you to look into this large-scale neural language model to understand what is happening inside it. So in other words, when it's making incorrect prediction, why it's making incorrect prediction, is based on which pieces of data. And again, there's a lot of machinery to do that, and I'm not going to go into all the details, but I'm just going to give you intuition into one of the approaches that we're currently developing. It's based on the concept of using global and local predictions, and the idea is that we're trying to cluster everything that is happening inside of these neural language models, and we try to relate it into code concepts. So like in this example, if you're trying to generate the rest of the code for piece of code which starts with public class circle, public static double, calculate area, and then you try to autocomplete this code, here inside the model, we would actually see what the model is doing in terms of the predictions. And as you can see on the right-hand side, at the bottom, you can see that we have three data concepts: data types, operators, and blocks. And you can also see probabilities. And in this case, what you will be able to see is that the model is doing actually a pretty good job in terms of predicting tokens which are related to blocks, but it's really struggling with predicting tokens related to data types and operators, okay? And this is some of the insight that we can give to analysts to basically point out particular code concepts that the model is struggling with given the training data. Also, we can use information like bugginess of code clones to, for example, to determine if code generator is working properly. In fact, we can do this with a little bit more sophisticated analysis, which relies on causal theory. Again, I'm not going to go into details. Hopefully, you'll see them in upcoming papers very soon. This is a work in progress, but the idea is that we can actually use rigorous statistical techniques like causal theory to do some really cool explanatory stuff to show how models may be potentially impacted by presence or absence of bugs or code clones in the training data. So now let's very briefly look into that second big direction: software engineering for deep learning, okay? And as Andrei Karpathy said, who is a director of AI at Tesla, is that neural networks is not just another classifier, because they represent the beginning of a fundamental shift in terms of how we write software. And of course, this is software that everybody understands. This is software 1.0. I'm not going to spend any time here, but this is software 2.0, right? Which can be written in a much more abstract, human-unfriendly language. In this case, these are just weights in this neural network. And again, a human is not involved in writing this code because human just provided an architecture and a lot of training data. And then these models have been actually trained on these data. But these models actually is code, right? Because when plugged into real software, they're going to do real tasks. So basically what this all means is that we can find programs or we can discover programs by discovering the correct weights of neurons. So all we need to do here is to specify some goal on the behavior of a desirable program. So we basically write the rough skeleton of the code, like in this case, neural net architecture, and then identify a subset of program space to search. And then we use computational resources at our disposal to search this space using gradient descent to find that version of the program that we will actually plug into our software. Like, if you want to train the network to classify whether a sign is a stop sign or something else, right? You can just train this component and then put it in your system. However, one interesting observation is when you look into real deep learning based system, and this is actually the study that is coming to us from Google, you can find that a lot of code and these systems contain a lot of technical debt, because only 5% of the code in the systems is actually machine learning code, and a lot of code is technical debt. So even modern systems coming from Google have a lot of technical debt in them. Also, you see that typically in these development processes, there are two groups of developers. One group of developers writing software 1.0 code or maintaining all this infrastructure, and then software 2.0 developers or data scientists who train these models. Also, when you look into the traditional software development lifecycle, and when you look into the software development lifecycle of these deep learning-based systems, you see that there are major differences, right? There are new stages of development for these deep learning-based systems where we define goals, we do data collection, data preparation, model learning, model integration, model management, so forth and so on. And now, of course, there are many unique challenges for developing deep learning-based systems. And again, I'm not going to go through all these challenges, but this is a really interesting topic. But there are obvious, very fruitful research directions for this community in particular that have to do with technical debt, understanding bad smells in these types of systems, addressing these systems, or understanding data dependencies. These systems are heavily reliant on pre-trained model. There is a big need to deal with configuration management issues, so forth and so on. So again, there is a lot of need to actually diving into these deep learning based systems. Hopefully I've convinced you that there is much more work that needs to be done at the intersection of these two areas, software engineering and deep learning, and it goes both ways. There is a lot of work that can be done, still can be done, when we apply deep learning to support many software engineering tasks, but also there is even more work in terms of trying to understand how we're going to build these new generations of systems which will have deep learning as underlying components. So of course, acknowledgements go to many of my current and former students who worked in this area. Again, this is a very passionate group. Also, thanks go to my current collaborators, Max DePenta, Gabriela Bavota, Oscar, and Adwait. So with all this, thanks for your attention. I know I took a little bit more time than necessary, but I would be very happy to answer any questions that you might have. Thanks a lot for your attention.
Well, thank you, Denis, for, I think, the outstanding presentation. I think you already got on the way already a question, which I think I will read to you, or maybe you can read even in the chat. So there was a comment that was the following: quite interesting and in between question. How do you see the retro work when compared with generating UI code for models, traditional model-driven style, or wireframes, as the design may not be hand-drawn, for example? This was one of the questions you got from the audience. Do you have any?
I see. So basically, when you design, when you have design as some sort of domain-specific language versus actual drawing. So actually, I don't know if I'm going to be controversial, but if you give me design in a domain-specific language, I think it's going to be an easier problem for me to solve. Because here, of course, if I have a lot of training examples, right, it's also another problem here. But the reason why I make this claim is because you will not need to deal with two completely different modalities of data, right? In redraw, we try to go essentially from image to code, right? Two completely different levels of abstraction, two completely different modalities, right? But if you give me a description of the graphical user interface in domain-specific language, it's going to be sort of text to text. So it's a little bit closer in abstraction. So I think that if we are able to get a lot of training data, neural machine translation could be quite effective in this setting.
Great. Meanwhile, if there are other questions, I would have one, for example, for you. Oh no, there is a raised hand. So you can write in the chat or intervene. Yeah, great. Hello.
Hello?
Yes.
We can hear you. We can hear you.
You can ask your question. Go ahead.
You explored to using your rich data to train redraw to aids UI generations. That's one question you got in the chat, Dennis.
So
Can I
sorry.
clarify that just a little bit as well? Sorry, I was the one that wrote that. But in terms of, I see that as, you know, you using redraw to help the developers take the proposals from the design team. But have you thought about kind of reverse engineering it and helping the design team to make the images in the first place? So being able to essentially backpropagate it either through like a natural language description of the interface itself, or as you said, you know, you have these hierarchies and you have all the labeled elements. You could even generate a sort of synthetic description and then make the original mock-up. Have you considered that at all?
Yeah, so thank you very much for the question. You're exactly covering a couple of different research threads that I didn't discuss in my presentation, but we actually have a little bit of work along those lines. So let me briefly give you two more pieces of the work that we've done, and you can find them on my website. So one piece of work actually we call GUI-Eagle, and it's a search engine for helping developers to find relevant mockups. So in that piece of work, we actually basically allow you to search for graphical user interfaces using natural language. So you basically want to, let's say if you're developing an app and you want to get an ideas of a mockup or design that you would like to be inspired by, but you can actually use natural language to search for those examples. So that's one. And second, we also have recent paper where we used image captioning approaches to try to automatically label, try to automatically extract and label functionality for the GUIs from actual images. And for that, we actually trained image captioning approaches. So these are two pieces of work that we already have along these directions. Do you have any other specific questions that I can delve into?
Thank you very much. I'll have a look at your future work for that then.
So the bottom line, there are still lots of very exciting opportunities here. Like what I didn't have a chance to discuss is feedback that we actually got from Google developers. What was that redraw is a useful first step, but they said in order for us to use something like redraw in our context, we would like to see it being also applicable in evolutionary context, right? They want also to see the case where you can quickly go to, for example, to the design sketch, and you can quickly update the design sketch, and you can get GUI hierarchy updated, and vice versa. We also want to make sure that you can update the hierarchy and also get those differences highlighted in the actual GUI. Okay, so you can easily and quickly go both ways, sort of in a very quick interactive way.
Okay, I think you answered very exhaustively, Dennis. Maybe you can finish the keynote, maybe in a more general question I had, since you had touched very broad topic. But what challenges from my point of view, I mean, what I would curious to hear from you, what are challenges you see on enabling trust on using AI for software engineering, and how this you think is related to human-computer interaction, or there is any relation with human-computer interaction? So wanted to hear from you.
Thank you, Sebastian. I think this is a critical question. And I don't want to simplify all this, but you know that there is we go through these boom and busts in research and in life, right? And what I call here boom is that we literally see exponential explosion of research papers that have been relying on deep learning, right? And what I've shown you in the survey is that In many cases, these papers approaches make sense, right? You really need to use deep learning. In many cases, you don't need deep learning, right? Or in many cases, you see lots of trivial and not very good cases where people use deep learning without too much knowledge or background, right? And they run into
Yeah.
common problems, so forth and so on. But your question really relates to what can we do to really enable developers' trust in terms of using these systems. And obviously, many of these solutions these days are implemented as recommender systems, right? So typically, they are like plugins in your IDE, right, that give you essential recommendation. And your question is that, why should I trust this recommender system, right? So like in this case of GitHub Copilot, why should I trust it? Because this recent study shows that it generates lots of security vulnerabilities, right? So that's why I think the work on interpretability is going to be the key to unlock this trust. So in other words, I as a developer need to know what this model was able to learn, right? And it needs to explain it to me in terms of concepts that I understand as a developer. So in other words, in terms of programming language, tell me why this prediction was wrong. Where it was because you did this misclassification because you're not good at in terms of predicting blocks or operators or other programming language concepts that I understand, right? So this is one part answer to the question, but it's not the only answer they have, because I think that another critical aspect is going to be HCI aspect, right? How do you create these systems so that they can actually learn together with developers, right? Yeah. So in other words, as a developer, if I see that this recommender system is able to take into account my relevance feedback, right? It's able to avoid these mistakes that I told it you should be avoiding, right? Then that could help us to bridge this trust, basically this trust gap, right? And I really think two key dimensions: HCI work, basically trying to figure out how we can make these tools interactive, how we can make them work with developer in concert, and also exposing some of the internals of these. Let's say if we're talking about large-scale neural language models, how can we help developers get a little bit more insight into what these models have been able to learn, right? In terms of programming concepts that we understand, so that we can actually understand if it's making a correct prediction. I have at least some sort of trace telling me that's why the prediction was made in this way. And if we made a misclassification, right, I want to understand why this model made this misclassification in terms of concepts that I can understand.
Okay, Dennis, I think you will get, or you got already some raised hands, but probably there is no really extra time for it. But I encourage all participants to contact Dennis directly via Microsoft Teams, later, MySpace, and via email. He has been doing a great research. I think it will be of your interest. Encourage you to not stop, but take this as a starting point for collaborating or conducting him. And thank you again, Dennis. We probably see in 4 or 5 minutes for who is going to present with short time, but I think it was worth it. Thank you again, Dennis.
Thank you very much. I really appreciate your attention. Thank you.
Thank you.
Hello. Okay, so we started the next important part of the workshop. It will be the research paper session. I know that the break was short, but we consider the keynote quite important part of the program. So I think it was important to give possibility to have some questions, some sort of important discussion. Just a reminder for who is going to present, it will be short. There will be 20 minutes for research paper, 15 plus 5, so there's quite a bit of time for question. For short paper, it will be 15 minutes, 10 plus 5 minutes, and for precision paper, it will be 5 to 5 minutes. So let's try to stay on the time, even though we try to always use the break as a way to give you all of you the time to present your work and present it well. So this exciting session of 4 paper has 4 interesting topics, and the first paper is from Peter Devine and Kelly Dinko. I think Peter is here, right? I see you, and
Hello,
probably
yeah.
you are going to present it, right?
So can I share my desktop then?
Yes, I just stopped sharing my screen.
Let's see.
Yeah, you should be able to share your screen.
Desktop, screen share. Okay, you can see this?
Yeah.
I'm guessing.
And not yet.
Share. Is this come through?
Yes, super.
Yeah. Okay, fantastic.
Great.
Right.
Floor is yours, Peter.
Okay, fantastic. Well, let's see. Hide this. Hello, everyone. Thank you to Sebastiano and Andrea for organizing this. Thank you to Dennis for his opening keynote. Apologies if my voice has gone a little bit. It's midnight and I'm a bit hoarse. So yeah, I'll try and get through this as good as I can.
Thank you for joining.
Yeah, cheers. Okay, so my name is Peter Devine, and I'm going to be talking about my paper entitled Unsupervised Extreme Multi-Label Classification of Stack Overflow Posts I wrote with my PhD supervisor, Kelly Blinko, at the University of Auckland. So I'd like to start off by talking about what Stack Overflow is, how we classify Stack Overflow posts, what extreme multi-label classification is, and then finally how we make that unsupervised. So first of all, what is Stack Overflow? I'm sure most people tuned into this know what Stack Overflow is, but it's a question and answer website for programming questions. You can ask a question and someone will answer it regarding programming in some way. So on Stack Overflow, at the time of this presentation, there's been more than 22 million questions that have been asked. It's vital for many developers. It's been widely studied for things like how code examples are written, how developers interact with each other. And just from a personal point of view, I don't think I would be able to code as well if I didn't have Stack Overflow. So here's an example of a Stack Overflow question. We've got a title here. And then a body which expounds upon the title in some way, describes more of the details mentioned within the title. And then finally at the bottom here, we have tags. So these tags describe the topic of the question. So this question here is about sending emails using PHP. So the tags here are PHP, email, mailing list, and mass mail. So this presents itself as a really nice, because Stack Overflow data is so open, you can query any of it at any time. This is very easy to attain. It presents itself as a really nice, obvious text classification data set. So previous approaches for classifying Stack Overflow posts have included using a smaller subset of tags. So Stack Overflow tags are distributed with a power law. So a few of the most popular tags are applied to a large amount of all of the posts. So for example, Python, Android, Java are used in a large chunk of all of the posts. So what these approaches do is they just train a classical natural language processing classifier to predict based on these smaller subset tags. There's also been work where a classifier has been trained on one set of tags, and then the system's been set up such that the similarity of unseen tags is compared to the tags used during training, such that inference can be done on unseen tags. So this makes the system able to adapt to new tags. So it's especially useful if new technology becomes available and suddenly a brand new tag is apparent. But our motivation for this work was, can we do this classification without using any tag training data at all? So pretending that these Stack Overflow posts don't have tags for training and then only using them for evaluation. This is to find whether we can somewhat usefully predict the topic of a sentence without having any topic training data. So the way that we thought we might be able to achieve this was by using text embeddings. So what is a text embedding? It's an embedding of some natural language text as a quantifiable vector. These are commonly used. So we have this sentence here: how can I sort an array? And it becomes a set of numbers. This is often used in downstream machine learning tasks. So these can then be used to essentially quantify a piece of text. So modern text embedding models are trained using most modern models are trained using Siamese networks. So these rely on pairs of data. So you have positive pairs of data that are semantically equivalent, and they're put through the embedding model and then embedded close together in embedding space, and then two sentences that are not semantically equivalent are embedded through the same embedding model and embedded far away in embedding space. So yeah, these embedding models often rely on paired data. So our approach for using these text embeddings to classify Stack Overflow posts was, first of all, we scraped 0.1% of all of Stack Overflow questions. We took the body of the questions, and we took all roughly 62,000 unique tags that were used for all of the questions. So not just our 0.1% subset, but 100% all Stack Overflow tags ever used. We took them as our unique tags for our evaluation. Now what we did was we embedded each post, and we also embedded every unique tag using our text embedding model, and then compared the embedding of the post to the embeddings of all of the tags, and did cosine similarity to find a ranking for each post. So this is visually depicted here. My Google drawing skills aren't great, but what we essentially get is we use the same embedding model for both posts and candidate tags. We have our vectors here, and then this returns eventually a similarity score for each tag, and then the tags are ranked by similarity, with the most similar tags ranked top, and then we take the top few tags as our recommended tags for our classification. So our approach uses recall as our tag ranking metric, or is the one I present here. So a recall at 1 would give you the percentage of all of the top recommended tags that were actually applied to the Stack Overflow post. So we test this using a couple of popular embedding models. The ones that I'll present here are the best performing ones from our analysis. So the top 4 here are all made available by Reimers et al. On the sbert.net sentence transformers platform. The models that we tested are based on either the MPNet or the Mini-LM language models. MPNet's a much larger model, Mini-LM's a lot more smaller and efficient. And both of these models are trained on the QA dataset. So the QA dataset is a question and answer dataset. So it has pairs of question and answer, or title and body, or question and duplicate question. And these are just from Q&A data websites, and this has contains a very large Stack Overflow component in it. We also tested models that are trained on the all data set. So these are trained on the QA data set plus other data sources like Reddit, source code, scientific publications. So these are trained on more data essentially. We also tested the universal sentence encoder, which has been trained on lots of different natural language tasks, such that it would be able to be theoretically better generalized to a novel embedding task in some way. And also LabSE, which is it embeds semantically equivalent text in different natural languages together. So in French and English and Chinese, all different languages, it would embed the same sentence in similar position. And these are compared against the majority baseline, majority class baseline. So this is the most popular tag would be the top recommendation, the second most popular would be the second, and so forth. So the results we have here. So we can see that the mini-LM and the MPNet models for the QA dataset perform best for small recommendation sizes. So for recommendation sizes of 1, 2, and 3, they perform best, and then the majority baseline performs better over larger recommendation sizes. So we can see that the QA datasets over all of the recommendation sizes perform better than the all models here. So the ones that are trained just on QA datasets perform better than ones that were trained on the QA datasets plus more. And we can see that the MPNet QA model performs, it gets about 16% accuracy on the top recommendation. So it's 16% of the time. Its top recommendation was actually one of the posts that the Stack Overflow post had applied to it. So yeah, we can see that the QA data sets perform better than QA data plus training on QA data plus other data, and they perform better than majority baseline for small recommendation sizes only. So is this good? Is this bad? I don't know. I would say 16% accuracy out of 62,000 possible candidate tags is not terrible, especially considering the fact that this is probably there's to my mind there's more of a chance of false negatives and false positives in that each Stack Overflow post has a maximum of 5 tags. You can only have 5 tags at one time, which would mean that yeah, there might be tags that were recommended that were actually applicable, but it didn't make it within the 5 tag threshold. False negatives are less likely, I would say, because that would include the author giving a tag that was not actually related to their question. Since they wrote the question, I think they would be quite well versed in which tags were appropriate. But I think that a trained classifier definitely would blow this out of the water, would just I don't think for Stack Overflow posts you should use this method for classifying Stack Overflow posts. I think what is useful though is applying this to other platforms that don't have topic tags. So if you have the topic tag data, I think you should use that. But if we don't have it, we've shown that training on more in-domain data, so being able to train on mostly Stack Overflow data is more effective than training on more generalized text embedding models that are trained on more data. And these platforms such as app reviews, forum posts, and tweets all have these natural pairs of text that can be exploited for making an embedding model. So app reviews have titles and content. You have questions and answers as well that can all be used to then train an embedding model to potentially do this topic classification. Yeah, so what would I have done differently if I was to do this again? while making this presentation, yeah, there was a few kind of regrets I had. So I really wish I'd done this by tag as well as by post. So what we did was take each post and then have a ranking of tags. I'd like to have also done get each tag and have a ranking of posts. So apply it instead of having a post classification task, having a topic search task instead. So you would search for a particular topic and it would give you the most applicable posts. One of my reviewers for this paper said that I should have included the title as well as the question body. I fully agree with that criticism, and I probably should have done that. I was a bit worried about maybe biasing the data in some way, but I think I should have included the title as well. And I would have liked to have tested it on the Spanish, Portuguese, Russian, and Japanese versions of Stack Overflow to see how multilingual models may have worked on it. And finally, I didn't see this, I didn't know of this model at the time of this research, but there are models that are trained purely on Stack Overflow, not just mainly on Stack Overflow, but just on Stack Overflow. That would have also been an interesting comparison. It would probably have added a bit more validity to my results. So yeah, here are some really good resources for working with Stack Overflow. You can query the dataset directly, and you can also download it from archive. It's a really good resource for this sort of research. Here are my references. They're not in alphabetical order because I would, yeah, stupid. But yeah, thank you very much for listening, and yeah, I hope to hear any of your questions.
So well done, Peter. I really like the reflective part where you sort of look backward what you have done.
Yeah,
really
rarely
seen in paper. Yes, you already have a person that would be interested to have a question. I guess Puya Rani from University of Bern.
Yeah.
So floor is yours.
Thank you very much for very cool presentation. And also, again, I should also mention the last slide was very interesting. I think this should be mandatory now for everyone that what we should have done. So I have two questions. One is that a lot of the models are trained on different similarity measures. So some use cosine similarity, some might use Euclidean, and this might impact, like when you basically use these models, do you think it has an impact?
Yeah, so a lot of these models, especially, I haven't seen so many that use Euclidean, but especially the difference between dotted models and just cosine trained models. There's a small disparity, but with both this work and previous work I've done with text embeddings, I don't find a massive difference, especially with when things are just using kind of relative rankings. The rankings don't really change that much usually. But yeah, it's something that I think should be cognizant of, especially if a model's trained on like a really exotic sort of distance measure, for example.
Yeah.
But yeah, I think it should be a consideration.
Another is how these models are trained. Sometime, let's say if a model is trained on Wikipedia data, which has never seen, let's say, some code snippet or anything, while with Stack Overflow data is very different. It has lot of code data, or even like apart from that, also their terms are very specific to programming languages. And how do you deal with those then when you compare these models?
So yeah, so some of the models that we tested, so yeah, so the top four here have all seen some sort of software engineering related work. Actually, these all data sets have also been trained on the CodeSearchNet data set, which is where it pairs the method description with the source code itself, whereas LabSE and use haven't been trained on codes to my knowledge.
And was there a major difference between like these models? Like if we go to the result, I want to see how
so you see the models that are trained more on Stack Overflow data perform better than especially the general ones. The general ones are still decent, but they're not nearly as effective. So I think it shows the the importance of training on in-domain data to effectiveness in this sort of topic classification.
And the last question I have, not really question, more suggestion, is since you realized afterwards that okay, there is a data set available on Hugging Face, what do you think about uploading your data set on Hugging Face? Like having there, I think it would be very nice. It would be very nice to have your data set there. Then more people can use it. It will be visible, and we can use it for more benchmarks.
I wonder. Yeah, I mean, so I've got my.
It's very easy.
Oh yeah, no, I've uploaded. Hugging Face is beautiful. It's an absolutely beautiful platform. I should do it. I've got my. I don't know if you Google the paper. I don't know. I haven't SEO'd it either, but I do have the replication package for this that is available on GitHub. Yeah, but in terms of getting at this data, all of this data is kind of available just through archive. So I suppose it's not very useful. I should do it. Yeah, no, that is a good point.
I think with Hugging Face it becomes more easy to compare, and it's more visible and more findable.
Yeah, I suppose the only concern is that it's just like 0.1% of all of Stack Overflow. Like I don't know. I think I just did it because of technical constraints. But I think having all 22 million questions would be sort of feasible. I wonder.
But people can extend data set from Hugging Face as far as they are in good shape. So that's not a worry, I think.
I wonder if there is Stack Overflow stuff already on Hugging Face, because
there are many.
Yeah.
There are.
Okay. Yeah, I consider it then. I'll think about it. I'll yeah. When I go into uni tomorrow, I'll have a wee Google and see if I could do that. But thank you very much for the question.
Thank you for answering.
Okay, I think we could. So the next paper is just don't leave immediately, Peter. Just waiting that the next speaker is joining live. So the next paper is Understanding Digits in Identifier Names in Exploratory Study by Anthony Peruma and Christian Newman from Rochester University of Technology. So I don't know, there is any other?
Yeah.
Okay, great.
Anthony is here.
I'm
Yeah,
here.
so
can you all see my screen?
yes, very well. I will have just a last question to Peter, but just try to closing, it's more about the, you mentioned if you were doing the study again, you will work on user view and other types of data, but just because this year we have the issue competition on GitHub issue, do you think that could be also a good context where you could apply your techniques or your approach is not really exactly what you wish to have?
No, I've looked at GitHub issues as well. They're really, really interesting. I think the thing is that I think pre-training on something like that would be really useful, but then I think fine-tuning on the given kind of issue GitHub issue labels would be still better. I think, as I say, I think if the data is available, but maybe pre-training on some form of kind of embedding using the title and the body of a GitHub issue might be tractable in some way. Yeah.
Super. Thank you, Peter.
Thank you very much. Cheers.
I know it's late there, but I think Anthony Peruma is more fresh, maybe, hopefully, than I think it's.
It's 9 a.m. over here, so yeah, we are fresh.
Super. Okay.
Okay.
The floor is yours for presenting your paper, Anthony. Thank you.
All right, thank you so much. So good morning, good afternoon, and good evening to my friends across the world. So my name is Anthony. I am a PhD candidate from the Rochester Institute of Technology, and together with my advisor, Christian, we are part of the Source Code Analysis and Natural Language Lab. So in this paper, we are performing an empirical study on open source Java systems to understand why numbers or digits are utilized in an identifier's name and how these numbers evolve when developers rename the identifiers. So let's get a quick background on identifier names and why they're important. So, the quality of an identifier name is paramount for effective program comprehension as they convey, the purpose of the code, right? So the stronger the identifier name is, the more you understand what the code does, right? Because poor quality names can lead to drops in developer productivity and may also result in developers injecting their defects during maintenance activities. So higher, so hence the higher the quality of an identifier name, the better it is. And when I say high quality identifier names, I mean these names are unambiguous and they reveal, it's very important that they reveal the purpose and behavior of the code that it represents. And, as Dennis mentioned in his keynote, developers create names, it's unrestricted. They can use any terms to create names, right? They can use, single characters or multiple characters to create names. So there's a lot of variety in identifier names, and part of this variety also includes digits, right? Developers use digits when crafting identifier names. Well, however, unfortunately, most of the prior work has focused mainly on names that have acronyms, abbreviations, or naming styles like camel case, underscores, and stuff like that. Even eye tracking to determine if underscores or camel casing is better. So there is very little in current literature about the rationale behind the presence of digits or numbers in an identifier's name. So therefore, the goal of this study is to examine identifier names containing digits in order to determine the part played by these digits in conveying the overall meaning of an identifier's name. And additionally, we are also interested in learning about any specific characteristics about these digits that occur within or occur inside of a name, inside of an identifier's name. In regards to applicability, we envision our findings utilized in tools or models that help developers with identifier name appraisals and recommendations, right? So, these are tools that tell a developer, hey, what, this name needs to change. This name is, looks to be bad, or, here are some, replacement names and so on and so forth, right? So anything to do with identifier naming and identifier name recommendations and appraisals, that's a good use case for, findings from this study. So to this extent, we formulated 2 research questions. In the first research question, we take a quantitative approach and examine the extent to which digits are present in an identifier's name and how they change over time. So we look at, the volume of such identifiers and how rename operations that developers perform, how do these rename operations impact such identifiers. In the second RQ, we take more of a qualitative approach to determine the rationale behind the presence of a digit in an identifier's name. And to this extent, we constructed taxonomy. So we constructed a taxonomy that helps you determine, okay, why is such a, why is a digit present in such a name? So these are the 2 research questions that we formulated for this paper. There were a few more that we were playing around with, but we felt that these, given the constraints, page limit constraints and so on, we felt that these 2 research questions are a good starting point in this study of digits inside an identifier's name. With regards to contributions, we have a few contributions. One is a taxonomy for the presence of such digits in an identifier's name. The next is basically details on how digits are present in an identifier's name and how these digits evolve. And we also have a discussion on the importance of digits in an identifier's name and also challenges involved in constructing this type of research. And towards the end, I will discuss some of the challenges involved when working with identifier names and especially around digits occurring within identifier's name. And additionally, our data set is also publicly available. So, please go through our paper. I've attached the preprint to the conference website, the conf.research website. The preprint is available, and in that preprint, details are given on how to access our data set. All right, so let's look at the study design before the methodology, right? So for this study, we utilized an existing data set we constructed for a prior study on identifier renaming. This dataset contains refactoring operations from around 800 open source Java systems. And we use refactoring miner to mine these refactoring operations. So for those of you who aren't aware, refactoring miner is one of the go-to tools when it comes to mining refactoring operations from Java systems. All right, so this dataset basically contains around 28,000 rename operations. So that's from all these 800 open source systems. So the next part of our study or the process involves filtering identifiers. See, our our study is about digits, right? So we need to only include identifiers that have digits inside within a name, and so that's where this filtering bit comes into the picture. And to do that, we used regular expressions to figure out, if a name contains the digits. So now once we obtain the list of identifier names containing digits, we then split the name into its constituent terms. And we utilize the well-known identifier name splitting program to perform this splitting. So next what we did is we had we manually examined the names in our data set, right? We wanted to see, okay, what do these names look like? And when we were going through these names, we noticed there is quite a lot of automatically generated code, auto-generated code in, in this data set. And and for example, most of these auto-generated code was related to Antler. So the problem with auto-generated code is that it basically skews our findings. So what we did is we looked at these auto-generated names, and we looked to see, okay, how can we identify patterns with regards to these names? What patterns are there for us to figure out, if a name is auto-generated or not. And then, by doing all this manual analysis, we came up with a bunch of heuristics that we applied to remove a majority of these names. So, we couldn't remove all auto-generated names, but we did remove a majority of these auto-generated names from our data set. So in the end, we were left with around 15,000 rename operations that contain digits in the name, which we then used to answer our research questions. Like I mentioned, the first RQ was quantitative in nature, and the second RQ was a qualitative exercise where we manually examined the identifier names. For the quantitative analysis, we used custom scripts, statistical measures, and so on. For the qualitative analysis, it was mainly manual. Like I said, it was manual review. My advisor and I, we manually reviewed a statistically significant set of identifier names, and to answer our research questions. So let's now quickly jump into our findings. So in the first research questions, we analyzed how rename operations impact the presence of digits in a name. So our findings show that developers frequently preserve the digit in the name when performing a rename. So it does not matter if the value of the digit changes, the new name will still contain a digit. So as seen in this example, there is still a digit in existence when a rename occurs. So, the majority of renames, they preserve the digits, and that digit can change, but still a digit is preserved in the new name. So then what we did is we looked at, okay, let's look at all the instances where the digit is preserved. And then we noticed that most names contain only a single digit in the name. And the number of digits in the old and new name are usually the same. And then finally, we looked at the position in which a digit appears in a name. And we noticed that position is usually preserved, and it's usually the second token. So as you can see in the last example, the position is usually the second token, or the second token in the name, and that position is usually preserved when developers perform a rename. So in short, for this RQ, we know the key finding is that digits are preserved when developers do a rename of an identifier, and that position in where the digit occurs is usually preserved. Let's look at a second research question. The second research question examines the meaning conveyed by digits in a name. So as I mentioned, we took a qualitative approach to answer this research question, where my advisor and we analyzed a stratified, statistically significant sample of names, and we also looked at the code associated with these names. Right? We didn't just look at the names; we also, did a trace link, and we looked at, okay, this name is used, in this situation in the code, and we looked at, the surrounding code to understand the context around the name. So our analysis yielded a taxonomy of 6 categories, showing how digits convey meaning to a name. So these 6 categories are auto-generated, distinguisher, synonym, version number, specification, domain, and domain or technology. So let's quickly look at these 3 categories. So the auto-generated category includes names that are generated by tools or IDEs. So for example, those of you who do like UI, UI development in an IDE, when you drag and drop UI control onto a form, you will notice that the IDE generates a name for that specific controller, right? So that's an auto-generated name. So these names sometimes, like in the case of antler, these names are sometimes not easily comprehensible, as shown in this example, and the meaning of the digits really depend on the generation technique. So next, it was distinguisher. So names that usually have a digit as a last token fall under the distinguisher category, where the digit basically performs the role of a distinguisher. So furthermore, there should be at least 2 identifiers having the same lexical name. All right. So in the case like audit log 3, so in this instance, there's also an audit log 1, an audit log 2, and an audit log 3. So the number 3 here is a distinguisher. So developers use these types of numbers to prevent name collisions at compilation time. Under the synonyms category are digits that are utilized by developers as substitutes for words. So for example, the number 2 is used as a synonym for the preposition to. So convert to list, right? The 2 is used as a synonym for the preposition to. Another use case, another example is the number 4. So 4 is used as a synonym for F-O-R. Next is developers also utilize digits to specify a specific version number of a system or library that is compatible with the code. And under the specification category, developers utilize digits to represent some sort of specification or behavior or characteristics related to the functionality of the system. For example, in this case, they meant this specific identifier is used, the number is used to represent the font size. So that's, it's related to the functionality or specification. And finally, it's also possible that a digit is part of a domain term or a technology term. So in this example, the attribute self for J log level is associated with functionality related to the self for J API. So the number 4 is over here. Right, so these are the 6 categories that we identified by doing our qualitative analysis on a stratified sample from the data set. So in summary, this study examines the presence of digits in an identifier's name and the evolution by studying the renaming of identifiers. And our findings show that developers consider digits as essential elements in an identifier's name and utilize these digits to convey a specific purpose. So moving on, we'll just quickly look at some key challenges and takeaways from this study. So like I said, auto-generated code is a headache when trying to do such studies. So since our work is really looking at how developers craft identifier names, auto-generated code really hampers such such studies. So because auto-generated code, if we were to consider auto-generated code, we will be making incorrect claims based on the data. Like when we're doing quantitative work or when we're generating samples to do a qualitative analysis, if we don't exclude auto-generated code, that's going to give us wrong results. So hence it's important to exclude auto-generated code, or at least try and limit the volume of such occurrences. And automatically detecting such code can be challenging, because generators, they don't use any standard technique. So it involves a lot of manual analysis looking for patterns, right? So in this study, we had multiple iterations of the data extraction process in order to determine what heuristics can we use to exclude such names. And the final challenge that we had was that there isn't much in terms of related work with regards to digits in identifier names. I mean, there's tons of work on identifier names and on code comprehension, but really not much on digits in an identifier's name. So we never had an opportunity to compare our findings, right? Because normally when we do a study, we always compare our work with related work to show, our work, ties in with existing work, or our work extends the existing work. But here, there wasn't really an opportunity to do that. We didn't have that luxury of comparing against any related work. And furthermore, our RQ2 findings show that digits can have multiple interpretations, right? Digits can be used to convey meanings for domain or technology terms or version numbers, synonyms, and so on. So it has multiple interpretations, and it requires analyzing the surrounding source code, right? You can't just look at a name in an Excel sheet and say, this name represents, such and such a thing, right? You have to, look at the source code, look where it's being used, the context around it, and you also need to know what the project is about. What is this project about? Because that's how you can figure out if a name is being used in the correct way or not. So the findings from our RQ support the community through a series of takeaways. The first takeaway shows that digits are preserved post-rename. So this is extremely helpful for the researchers working on tools and models and around improving name appraisals and recommendations. Furthermore, there are also instances of developers using generic terms like arg and parameter and then appending a digit. So tools can look for such instances and inform developers to provide a more specific name, a name that reflects its intended purpose. The second takeaway is about the meaning conveyed by digits. So our findings can assist in determining if a digit is related to its associated code. Furthermore, the digits can also serve as building a catalog of technologies or standards or domain terms utilized in the project, which can serve as input to project or code summarization. And before I quickly wrap up my presentation, I want to quickly introduce our Identify Name Structure Catalog our lab has been working on. So this is a public resource for educators and researchers who want to learn more about identifier naming, and also if they want to find any materials that they can use for their course. The catalog basically provides a summary about naming practices. It includes definitions, part of speech tags, linguistic terminology, common naming structures, linguistic anti-patterns, and also a bunch of examples. The catalog is built using findings from our past studies and also work done by other researchers in this field. And we encourage the community to contribute to the catalog, and we are open for more suggestions and ways to improve it. And lastly, if by any chance you are attending ICSE, do try and attend our journal first presentation. It's about our ensemble part of speech tag for source code identifiers. Yeah, this is this is about how we built a part of speech tag that's geared just for identifier names, right? We all heard of the Stanford part of speech tag, which is really great for general text like Wikipedia and stuff. So this tagger is built for source code for identifying names. And we will also be in person in Pittsburgh, and we will demo this tagger along with some other identifying naming plugins. So do come meet us, say hi to us, and we might just give you a little something for coming and saying hi to us. So if you're attending ICSE, this is you shouldn't miss this presentation. And with that, I've come to the end of my presentation. So if you want to contribute to the naming catalog, or if you want to learn more about what we do, or if you want to contact us, please visit our website at scanl.org. So thank you so much.
Thank you, Anthony, for proposing this new notion, which an identifiers I never heard, or let's say before this paper. And I'm glad that there is also some tool automation. That's great to hear, and then people can follow up on your results. You already got a person interested to talk to you, which is here, Puya. Maybe there will be others, but maybe Puya, you can go first.
Yeah.
I have a very small question. So with this digit preservation, so we could see from your research that yes, developers have a lot of interest in preserving digits, but you must have seen a lot of heuristics. Could you see that which particular location they write these digits, like initially and towards the middle, so that the next auto-generated approach can somehow measure the location and then build some automation towards it? Could you see some patterns with digits?
Yes, we did that. Yeah, we did see. So the digit is usually, in most cases, it's usually the second token in the name, right? So that's kind of where the digit occurs. And then when the developer does a rename, that position is still maintained. So the developer either adds terms, after the digit, or maybe removes a couple of terms after the digit. So the position number 2 is usually where the digit occurs.
Okay, that's very interesting. Do you have any insight? Why is it so?
One reason.
Could you talk to some developers?
So that's something we need to do. We need to so this was an exploratory study, but one going forward, to working closely with developers to figure out a rationale as to why they prefer the second position is a good option. Another reason could be because in the case of distinguishers, developers just add a digit at the end, so they create a bunch of identifiers with the same name but just add the digit at the end, incrementing it. So that could be another reason as to why the digit appears in the second position.
Yeah, makes sense. Thank you.
Thank you.
Okay, so while waiting potentially other question, I will at least ask the next authors to join. Maybe from the paper is from.
I have a question,
yeah.
Sebastian.
Go ahead, Andrea.
do you plan to implement an automated approach for supporting program comprehension on identifier numbers?
So that's part of the plan. So right now we're working on a plugin, an IDE plugin to do identify name appraisals and recommendations. We haven't as yet incorporated the digit scenario into the plugin, but that's working. That's currently work in progress. So if you happen to attend ICSI in person, we can show you our tool, how it works in the IDE.
Okay.
And then you can see how incorporating such digits into the tool will be pretty straightforward.
Okay, thank you.
So great. If you have other questions to Anthony, I'm sure they will. I think you can follow up on with him, and there is here the link to his tool. So please follow up with him. I think it's time for, I see already some of the others coming. Dominic, updates, and
Hello.
I think you're going to present your work on From Zero to Hero, generating training data for question to cyber models, with co-authors by Nico Ockgeschwender from
That's
Rhine University Wise. So
right.
I think we're ready to see your presentation on the stage. Thank you very much.
Are you able to see my screen right now?
Yes.
Yes, all right.
Yes.
Okay, thank you very much. Welcome everybody. My name is Dominik Opitz. I'm here on the left. I'm from Bonn-Rhein-Sieg University in Germany, and together with my co-writer Nico Hochgeschwender on the right, we proposed the short paper which can be used to generate training data for question to cipher machine translation models. So to understand what we did, let's look at a typical scenario in a company. Imagine the company, and then a CEO of this company has a question about some numbers or information about the company. Now the CEO has to go to the IT expert, and the IT expert has to formulate a database query to query the database and get the results back to the CEO. Now this process is time consuming, it is prone to errors, and therefore generally expensive. What would be much better is to use or to put a neural machine translation model into place, because this model would be able to automatically translate the question from the CEO to the database query and then get the result much faster. The thing is that these models do actually already exist, in particular for databases, or mostly for databases which are relational and which can be queried using SQL. The problem is that we do not always want to use relational databases in our company. Instead, we often see that, for instance, graph databases are becoming much more popular, especially when we're working with big data in real time, when we want to integrate intelligent systems into our overall system, or whenever the data representation of relational models is hitting their limits. So in our little scenario down here, really what we want to see is instead of a relational database, we want to see a graph database. The scenario we just looked at is a typical question answering scenario. And question answering scenarios are solved in many different ways. We can use template filling, we can use information extraction, we can use external knowledge bases. In our work specifically, we focused on the use of neural machine translation models in combination with the graph database Neo4j, which is queried using the database querying language Cypher. The problem with this setup in specific is the training and the data sets. So machine translation models require a huge amount of training data, and this data needs to be in parallel. That means that we have the natural language question on the one side, and we have the corresponding database query on the other side. These data sets do exist for other languages like SQL, but they do not exist in this form for Cypher. There are other ones, such as, for instance, web questions, where we have a natural language question on the one side and we have textual answers on the other side, or we have DBNQA, which you might be familiar with, where we have questions on the one side and then a Sparkle query on the other side. But this is not Cypher. We always need to map to Cypher still. We always need to bridge the gap between the natural language question and the query, the Cypher query. In our work, we propose an architecture which can be used to generate such missing training data specifically for question-to-cipher NMT models. So existing approaches in this kind of field often perform data augmentation instead of data generation. That means that they typically start with an existing but low resource data set such as WikiSQL, WikiSQL. WikiSQL is a data set where you have natural language questions on the one side and you have corresponding SQL queries on the other side. And these approaches take these SQL queries and then train a recurrent or any neural network to predict the corresponding question based on the SQL query. And then they can go ahead and generate more SQL queries and then iteratively come up with a corresponding question to enhance the data set. Our architecture is similar to these approaches as we also try to create a question based on a given query. However, our architecture differences from these approaches because we do not adopt a purely sequence-to-sequence learning approach on some initial data set simply because we do not have one. Instead, we make use of, in this case, also WikiSQL and also intermediate representations so that we can overcome the bridge between or that we can bridge the gap between the language, the natural language question and the cipher query. One second. The first step, we have the pre-processing. We take WikiSQL, the SQL dataset we just talked about, and we take the SQL part of the dataset. Now, for each of these SQL queries, we generate a fixed pattern-based pseudo question as an intermediate representation. Like I said, these are fixed. We previously manually defined those natural language patterns. Now, for each of those pseudo questions, we still have the original question from the dataset, so we can take this and train a recurrent neural network, which is capable to further enhance the pseudo question further to the original question of the dataset. In the second part of our architecture, you take an existing database of your graph database, a Neo4j database. The first step is to iteratively generate a list of cipher queries from this graph. This is a straightforward script-based script you can just execute. Now, for each of these cipher queries, we can use the same kind of natural language patterns to generate a pseudo question. And because these follow the same style and the same conventions, which we use in the pre-processing step, we can take the previous model to further enhance those questions to formulate a proper natural language question and be better readable. Let's look at some of the results. In our testing, we took the default graph from Neo4j, which is movie graph. And for instance, here we generated a cipher query for which the pseudo question reads name or name of person, where person name equals Philip Seymour Hoffman in descending order by person name. Now, the enhanced version of this question reads, what is the name of the Philip Seymour Hoffman in descending order? And here we can see that the question, the enhanced question, is shortened and it makes more sense to the reader. In the second example, we can see that other results are or might be more flawed than the previous one we just looked at. We actually often found that the enhanced version of the question is missing important attributes, which might lead to incorrect predictions in the future, but we're going to look at this specific issue in just a minute. For our evaluation, we adopted a component-based approach. That means that we trained a model to predict a cipher query on all of our enhanced questions. And then for each of the cipher queries, we counted the correct or the number of correct and incorrect subclause predictions. For instance, how many times did our model correctly predict the label of a node, or how many times did we correctly predict the value of the where clause? The numbers are very promising, and in the next slides, I want to focus on the most critical parts of the evaluation. First of all, like I've hinted before, the model had issues correctly predicting the attribute of the return clause of the query. And we found that often the enhanced version of the query is missing important keywords. You can look at the examples here on the right, for instance, name the is Allison, or name the is Lori Petty. Obviously, there's something missing, like maybe they name the name or name the birthday or name the title. But this way, like it is here, the model can only guess what the correct attribute might be, which obviously leads to more incorrect predictions as when the attribute would be included in the example. Similarly, we found that often we had incorrect predictions of the value of the where clause. And this happened often, or most often, when the value is a long string value, possibly even with punctuation, like the ones down here. We think that these long string values introduce a lot of unknown tokens, which potentially confuse the model and therefore lead to incorrect predictions. A final fundamental challenge I would like to address is this one. Consider the example on the left where a user posed the question, name our person where the hobby is surfing. Now in our testing, this did lead to a valid cipher prediction. However, if you now replace the word person with the word people, the cipher prediction completely breaks down. And you might already know why that is. It's because the word people was not present in the graph database which we used initially, and therefore it is unknown to the model. Now this problem is obvious, it's easy to understand, but it is crucial to see why it is important. Because in a future scenario where this architecture might be used, a user will not use the language of the database, a user will use natural language. And natural language is full of synonyms, full of abbreviations, and just any kind of other variety. In conclusion, we proposed an architecture which can be used to generate targeted parallel training data specifically for question-to-cipher machine translation models. We made use of pseudo questions so that we can overcome the problem of the missing initial data sets. In the future, it might be advisable to integrate these cipher-specific relationships into this architecture. Specifically to overcome the fundamental challenge, which I talked about just on the previous slide, it is probably a good step to apply some kind of graph representation learning into the architecture. And together with the use of other data sets and also the inclusion of, let's say, external semantic information like knowledge bases, the generation process of the questions could really be enhanced in terms of both quality of the questions and also the variety. This concludes the presentation of the architecture, and I think we have a few minutes left for any discussion. Thank you.
Thanks for the presentation. It was a good mix, of technology from databases, from other language. I think I really liked a lot of discussion, but given the time, I give the token to the first person that has a question, Rafael.
Yes, thank you very much, Dominic. I can tell you in the software working industry and these kind of queries I'm getting all the time. It's a very elaborate process trying to answer these questions. And that also, from that comes my question. In your initial slides, you present one example query, which I thought is very interesting. You say, you ask the question, who is our most valuable customer? Mm-hmm. My question to you is, how does the model know what a valuable customer is in my company?
That is one challenge. So the thing is, with this architecture, you can use the database of your choice. So you can apply to your specific company, and you need something, or you need some way to know that, like you said, the term "who is the most valuable" translates, for instance, to the customer with the most revenue, or the customer which has the most communication with your company. That is indeed a big challenge. And I think in this specific scenario, it also comes down to the data set you use, because in the end, you train a data set to predict a question based on a query. So if this formulation is not present in the data set, it is difficult for the model to know. WikiSQL in retrospect is not the ideal data set to use for this. I don't know, are you familiar with WikiSQL by any means?
No.
Okay, it is actually mostly about sports and politics. So maybe here a combination of a much bigger variety of questions might be more sensible. But that is indeed a big challenge, which might have to be addressed in the future as well.
Thank you.
Okay, I think while I let the new speaker, Britta, to share his slides, I could have another question actually to you, Dominic. Yes. It's very low level in this case compared to Rafael. It's more, you talked about pseudo queries and similarities, and we are in natural language base of a workshop in software engineering, and I was wondering if you did observe any NLP linguistic patterns or recurrent linguistic pattern in these pseudo queries? Do you have any thought about that? It's not really the case.
You mean whether the patterns repeat in the generation
Yeah,
process?
from a linguistic level, you did see
Yes,
similarities that you could
that
actually
is,
reuse somehow.
I can, well, I formulated the pattern. So there's things like name the, so I don't know, let's just look at one of the examples real quick. I can show you.
Yes.
For instance, let's look at this specific example. The pattern here was name all, and then here the name right here is an attribute. So this might be something like name all and then attribute of person is an entity. So we have the pattern name all attribute of entity, where person is the entity again, name is an attribute. So we kind of stick these patterns together with a combination of attribute, entity, comparator, value, and then we come up with different formulations. In specific, I mentioned web questions, and what we did is we extracted all the questions from the data set, and then we ran a pause tagger across the data set to come up or to find the most used patterns for this. So we can't look at how many times did this formulation name all, or what is, or how many times come up, and then these are the most popular patterns which you can use.
Great. Thank you, Dominic. I think it's time for the next speaker, but thanks a lot again for your questions and your presentation. It's time for Peter to present from Drexel University automated identification on informative code in Stack Overflow post in relation with some of the talk already have been discussed as a quite complementary. The floor is yours.
Yeah, just, can you give me 1 second? I'm trying to share the screen and
yes, take your time. I know in Macs is always a bit problematic. I have the same problem. Probably you need even to go out from the Microsoft Teams. Could happen.
Yeah, it could. So let's see. I did want to try before, but
But actually, we see your screen in reality.
Yeah.
Oh,
we
okay.
actually already see your screen. So I wasn't sure what you wanna.
Okay. It prompted me to open my settings, and I was like, okay, what's going on?
No. It's all working. It's all working.
Okay.
If you make it to full screen, it's all fine. Super.
Yeah, I often I don't use Teams that much, so I'm not very familiar. So sorry about that.
But even if you use, but still, please.
All right. Well, thank you, and good morning, good afternoon, good evening to everyone who's attending this workshop this Sunday. So I'm going to talk about my work on automatic identification of informative code in Stack Overflow posts. And just to introduce myself, I'm Preetha Chatterjee. I'm an assistant professor at Drexel University. And so I'll start with this talk with a little bit of why we are trying to do this work. So a little bit of motivation, as in many of us, as we already know, that Stack Overflow is a great resource for us, for any software developer. But all of us are probably aware that there's so much information in it. So it's really difficult sometimes to find relevant information from it. So one of the papers by Zhu et al. Actually found out that if it's a really popular post, it can take about 30 minutes to read all the questions and the answers at a standard reading speed. In one of our previous work, we tried to understand that, okay, given all this information, how much information do we actually need? And we found out that only 27% of code in a post is relevant for a software developer to understand and apply the relevant information to their context. So There have been several studies with which researchers have tried to help Stack Overflow users with this information overload. Specifically, there has been some work on reformulation of queries, automatic high quality post detection, automatic tag recommendation, and most recently there was a paper which was about identifying Q sentences that could help an user to navigate a Stack Overflow post better. But none of these studies actually focus on identifying specific or informative code segments in a post. And that's what we are trying to do in this paper. Specifically, we focus on identifying pair of problematic and suggested code pairs from Stack Overflow. So what do we mean by that? So in the left, you see there's a typical Stack Overflow post for space constraint. I'm just showing you one answer, but there are generally more answers to one question. And so oftentimes we find that both the problematic and suggested code are in the answer, as you can see here, the one that is highlighted in blue, right? So the solution poster is giving a very targeted suggestion, as in change this part of your code to something that the person suggests. Now this is one format. The other possibility is often that the change is not that targeted, right? Like you cannot explain that, or it's just not maybe one line change, or it also depends on the solution poster. So oftentimes we would also see that there is a question, a pretty big question, which contains that what the developer had been trying to do, followed by some code segments, and then in the answer the solution poster would also give a large snippet of code as a suggested solution. Now it's often difficult to find out that what exactly is the change that we are required to do here. And also it's very difficult for someone else to understand, okay, here is this information, but how can I use it to my context? So here what we are trying to do is that automatically trying to design a system using natural language based techniques so that we can automatically find this problem and suggested code pairs. So for the first type, we see that when a solution poster is giving out very targeted changes like this, there are recurrent linguistic patterns that follow. So from our data set of 2000 Stack Overflow posts, we found that there are these 5 patterns that occur the most. So for example, the one that we see here is the first pattern of change problematic code to suggested code. So this is for most of the times using these patterns is sufficient to automatically identify problematic and suggested code pairs when they are both located in the answer. Now for the next part, we decompose this problem in 2 parts. So the first part is where we first try to understand or identify the suggested code from answer. And here we first use a tool called Deca, which happens to be a tool and paper designed by our organizers, Andrea, Sebastiano. Great paper. Been a fan of that paper since a grad student. First tried with that tool, worked pretty well. But specifically from this tool, we use the solution proposal category to automatically identify the suggested code in the answer, but there were still some limitations, right? So it could not identify all. So what we thought is that, okay, how can we improve that? So as a next step, what we are thinking here is that we often notice that automatically identifying short imperative sentences would be an addition that we can do here, and that helps us identify more of this suggested solution phrases in this answer. And the suggested code generally is followed by that phrase. For the next part, where here we are trying to identify the problematic code from the question. So in the first part, what we do is that at this point, we already have the suggested code identified from the answer. So here we first extract all the code elements from the suggested code, and we try to see that if these code elements occur in the question code as well. So we go each line by line and try to find out lines of code where these code elements are occurring. And if we find that there is a commonality, we would identify that line of code in the question as a potential problematic code. And then we use a pair of textual similarity measures to see if these lines are similar enough. So the intuition here is that if these are the pair of suggested code and problematic code, it would be similar enough with certain changes. So if the comparison crosses a certain similarity threshold, we would consider that as a problematic code. So this is still comparatively, like we are not, this is a short paper, so we are not done yet with the full evaluation. So basically what we tried to do is that, okay, we got some interesting results, so let's find out that if this is at all going to be useful or not. So as a pilot preliminary survey, we first asked few software developers that a survey which actually had two questions. So the first question was that what parts of code in a Stack Overflow post would you recommend highlighting or helps you to find or focus your attention on. So the most prevalent answers that we found here is that they suggested that the lines of code in the question that is responsible for causing a particular error or exception, and in the answer the targeted fix, because oftentimes the answers contain a lot of code segments and it's really difficult to find the exact targeted fix that is required to solve that problem. And the second part of the survey was a kind of a feedback where we provided them with a set of highlighted Stack Overflow posts and asked that, okay, if we give you a highlighted post like that, maybe if we design a highlight tool, automatic browser extension, or some sort of highlighting tool, would this be useful for you? So here we found that 56% people indicated that it's very useful, 32% indicated useful, and the rest 12% said somewhat useful. So this is this result shows that, okay, this is necessary and people struggle with finding relevant information from Stack Overflow. So we are excited about this work. So in summary, natural language-based approaches show promise to extract problematic and suggested code from a post. And this work could help improve the Q&A forum interface, such as Stack Overflow, by designing any browser tool or any highlighting tool as such. It would also help to guide tools for mining forums, improving granularity of traceability mappings involving forum posts, and so on. So, yep. Thank you, and I'll be happy to take questions.
Oh, wow, that was fast. You already got one. But
Yeah.
no, that was an interesting topic. If there will be time, I will have one question or two. But I think first the others.
Yes, we have a user that raised the hand.
Oh, me? Yeah. Sorry. Cheers.
Yeah.
Please go ahead.
Sorry. Thank you very much, Preeta, for the talk. I thought, especially, having done some stuff on Stack Overflow, I thought it was really interesting. Could you talk a little bit more about how you plan to do your matching for code similarity? Because yeah, having worked on some like kind of code embedding stuff as well, I can see some applicability potentially for that.
Yeah. So well, thank you for the question first. And because in this work, we know that there are like several code similarity techniques that we can use, but we try to approach this from an NL-based approach, So it's basically we use just text similarity measures. So it's a edit distance measures and to see that without using any of code similarity measures, what we can achieve using just NL-based similarity measures. So that's the goal, but I think we could definitely explore more code similarity based approaches as well. But what we were really interested about was seeing that without using any of that, what can we do by using just textual similarity based formula and stuff. So that was the goal here.
Cool. Cheers. Yeah, no, I just wonder with kind of text and code. I don't know if you. I definitely appreciate kind of keeping it simpler, like with just doing edit distance, Occam's razor and all that. But if you are looking to use like neural stuff, there are ones where they have text and source code embedded together. Potentially, that could be like a nice halfway house between the two.
Yeah, that would be interesting. Yeah, well, thanks for the suggestion. So this is still in the works. So
no, thank you very much. It seems like cool research. Cheers.
Thank you.
Sebastiano, the mic.
Did you have a question, Andrea, that you joined, or?
Nope. Everything is clear.
Yeah, just a question for you, but it was more out of curiosity. So now you separate informative posts from informative ones. This reminds me a bit of this work with Andrea on separating informative reviews from App Store and informative one. The next step we did was summarizing user view. So I was wondering if you want to query second floor, there's a lot of useless posts, but you want to have gotten an answer to a question. Do you think that summarization could be the next step of your work, or not really the direction?
It could be. I think there has been some work in answer like summarization, especially the work that the work that I started my presentation with, Zhu et al. So their paper was mostly about, since there are so many answers in Stack Overflow, how can we summarize important answers? And so I think it would be really good to compare our technique, after we do this and then summarize, and with their technique to see how the summaries would differ, right? And how that would be an interesting idea to pursue. Definitely, yes.
Yeah.
Wait, I had another one, since unless there are other people, there's still a couple of minutes. We will have 5 minutes break until 55, but I had another one that was out of curiosity. It's, we are in this workshop on natural language base with this tool competition. I like to refer to it intentionally. So, or also in GitHub, you get sort of relevant post or the pull request even, or issues. Do you think that it would be too hard to move there, or it's not really the same thing? You get code, you get also comments.
Yeah.
I understand.
Yeah, so I guess
you don't need to say yes. I mean, just saying, like exploring. No.
Yeah, so I would. Yeah, I mean, that would be. So, is your question that if we want
if you think that what you have done could be applied to GitHub issue or GitHub pull request, because also that you have description, you get answered, you get also the code in some cases.
Yeah.
I think we could. Especially for issue requests and pull requests, issue reports and pull requests. Only thing I would be a little bit skeptical about would be some kind of chats, because in chats there is no full sentence, right? There is you can't do part of speech tagging. It's always a limitation. So I think this work could translate well, or I mean we have to see, but there is a possibility to use it in issue reports and those kind of artifacts. But of course there will be limitations based on the type of artifacts.
Looking forward to it then.
Yeah.
Okay,
Yeah.
I think we take
This could
5
be
minutes.
a call.
Yeah.
This could be a call for
Next
research,
event.
for tools, for yeah.
Okay, I think it's good to take a break of 5 minutes. We come back in
Yeah.
55. There will be the tool competition for Rafael and Oscar Chaparro, Africalis. So see you in a moment. Then thank you again, Rita, for your talk,
Sure.
and everyone else. Bye. Works well.
Can you guys hear me
Yes, yes.
and see me? Good.
Yep.
Let me try sharing as well.
Yeah, and I think you can already have your like beginning slides, basically, waiting until the next few minutes.
Sure thing.
By the way, the quality of your camera is impressively good, Oscar. I can really.
I'm
Wow.
using my phone actually as a camera, as a webcam.
Wow.
So do you see my screen, guys?
Yes,
Yeah.
yes, definitely yes.
Excellent. Cool.
So we'll suddenly disappear, then I'll let you, lead the show for a bit.
Yeah, sure. I'm trying to see if we have the authors of the tool competition of the tools. I see Giuseppe. I see Mohammed. Let me see who else. Alexander. I see Alexander. Is Shikar here or Tushar? No. Okay. And Malihe, it's here. I think so. Cool.
All right. Hello, everybody. Welcome back. We'll now continue with the tool computation. So my name is Rafael Calles. I'm an industry practitioner, and I love research collaborations. That's why Sebastian and Andrea invited me here to co-chair the tool competition with my colleague Oscar. Oscar, do you want to say something about yourself?
Sure. Hi there. This is Oscar Chaparro, assistant professor at the College of William & Mary. Excited to be here to hear all the teams that submitted their fantastic tools. I work on the issue analysis, bug report analysis a lot, so this is quite relevant for for me and for my team.
Cool. Thanks so much. Okay, I will give an overview over the tool composition. Right. So the goal we set is to develop more accurate models for issue classification, like those you can find on GitHub issue trackers, for example. We have provided a baseline model based on past work. That is Ticket Tagger, which makes use of the fast text model. We did publish a very extensive data set of over 800,000 issue reports, spanning over 127,000 GitHub projects. And we're very excited for the 5 teams that have entered the competition. All right. Few more details about the problem we're trying to solve. Okay. So, as I mentioned, the tool competition wants to strengthen the issue management process. Issue trackers became a necessity for the modern software engineering process. Yeah. In many cases, they are the central knowledge repository of feature requests, bug reports, and questions asked within a software project. These artifacts are then put into backlogs, for example, given priority, assign the person to work on, implement the feature, fix the bug, etc. The issue management process might differ across projects, teams, or organizations. However, determining the type of the issue remains a common activity. Okay, so by convention, often the person that submits the new ticket also is responsible for assigning, let's say, appropriate labels or metadata. This practice, however, is not feasible for all software projects. Open source software projects, for example, allow everyone to open a new ticket, but assigning type, priority, or a developer to work on the ticket is reserved for maintainers only, for good reason, I should say, right? So the issue type triage process becomes a more resource-intensive and time-consuming activity the larger and more popular a software repository becomes, right? We therefore set the goal to help maintainers triage new issue types by automating the issue type classification process. So the baseline we provide, based on recent work, which you can find below the slide, model based on fast text, which has been pre-trained on existing issue titles and descriptions, and then given a newly classified issue, we even assign the label, assign between the labels bug, question, and enhancement. The dataset that was provided for the benchmark encompasses